In the following example, we're going to be tackling an application question that requires a knowledge of how to find the equation of a normal given a specific point on a curve. We're told that a curve has the equation y equals 4 minus the root of x, which I'm going to write as x to the half, and 4 minus x to the half is all cubed. We're going to need to find the normal at the point P, 4, 8, and the normal at the point Q, 9, the equations of those straight lines. And we're going to need to find their point of intersection at the point R, and then we're also going to have to find the area of a triangle, PQR. Let's start off with part A, where we have to find the coordinates of the point R, where the normals at these points P and Q intersect. First thing we'll have to do is we're going to have to find the gradients of a tangent at these points and then use that gradient to find the gradient of the normal. And to do that, we're going to have to differentiate the function y, which is a function in x, and we're going to have to apply the chain rule. Okay, and just to go over how we've applied the chain rule, we have differentiated the outside function by taking the exponent of 3 and placing it in front of the bracket and then dropping down the exponent on the bracket down by 1. That's differentiating the outside function. Then we have to multiply that by the differential of the inside function. The constant 4 falls away, and then the power of a half above the x becomes the coefficient of x, well, multiplies the coefficient of x, and then the exponent of x drops down by 1. So we get times by negative a half, x to the power of a negative half. And I always advise writing these functions in their simplest form possible, which would mean not having any fraction exponents or any negative exponents wherever possible. So because we see we have a negative exponent on the x, we know we're going to have a fraction. This whole expression can be expressed as a fraction. In our numerator, we're going to have 3, 4 minus root x. So I've changed that x to the half back to be written in the form of root x squared. It's timesing a negative, so we're actually going to have a minus in front here. And in our denominator, we're going to have 2 root x. So that x to the power of a negative half is the same as a root x being in the denominator. That negative a half places the root x in the denominator. So this now is our differentiated expression. Next step is to find out the gradient of a tangent at point P and the gradient of a tangent at point Q. Then we will use those gradients of the tangents to find the gradients of the normal. So let's start off with the point P. So when x is equal to 4, the gradient of y, dy by dx, would be equal to 3, 4 minus root 4 to the power of 2 all over 2 times root 4. What we have done is we have taken the x-coordinate of the point P and we've substituted it into the differential of y to find out what would the gradient of that function y be when x is equal to 4. If you use your calculator to help you out with that, we should get the answer of -3. So that means that when x is equal to 4, the gradient of y will be -3. Let's also work out what the gradient will be when at point Q, when x is equal to 9. So there we would follow the same process, except this time we would substitute the point 9 into our differential, the x-coordinate of 9 into our differential. Okay, when we compute all that using a calculator to help us out, we'll get an answer of a -half. Okay, so that now that we have differentiated our function and we have found the gradient of a tangent to our function at the point P and at the point Q, we have set ourselves up well to find out the equations of the normals at each of these points. Let's start off by finding the equation of the normal at P, which is the point 4, 8. To do this, all we would need to say is that y subtract 8 is equal to 1 over 3 x minus 4. The 4 and the 8 in their respective places came from the coordinates of P, the point where the normal crosses the curve. This value of 1/3 is the negative reciprocal of the gradient of the tangent. The gradient of the tangent when x is equal to 4 is -3. Now the normal is a perpendicular line to the tangent, so we have to find the reciprocal of the gradient of the tangent. That's how we get the third. And we have to change its sign because the normal is perpendicular to the tangent. Yeah. And then rearranging this to get y as the subject, we'll have y equals a third x minus 4 over 3. That's just distributing the third into the bracket. And then we have to plus 8, which plussing 8 is the same as plussing 24 over 3. 24 over 3 is the same as 8, and why I chose to make it 24 over 3 is just to make the addition of those fractions easy. So we've got y is equal to 1/3 x plus 20 over 3. Some of you may prefer to work in decimals. I, for one, often prefer to work in fractions. It keeps your answers more accurate. Now, we also need to find out the normal at Q, which was the point 9, 1. We're going to follow a very similar process. This time we would say y minus 1 is equal to 2 x minus 9. And hopefully we are now familiar where all of these values came from. The minus 1 is the y coordinate of Q, is subtracting the y coordinate of Q. Minus 9 is the subtraction of the x coordinate of Q. And this figure of 2 came from the negative reciprocal of a negative half. So the gradient of the curve is a negative half when x is equal to 9. So the gradient of the normal would be the reciprocal of that, and the sign changed. And then simplifying this all out, getting the equation with y as the subject, we'd end up with y equals 2x minus 18 plus 1. So we plus that 1 to both sides after having distributed the 2 in, and we get it in its final form of y equals 2x minus 17. Now that we have the equation of both normals, we can find the coordinates of r, which is the point at which these two lines cross. To find the x-coordinate, all we need to do is equate the right-hand side of each of these equations to each other, and then solve for x, and we'll find the x-coordinate of where they cross. First thing to do would be to multiply everything by 3. So we get x plus 20 equals 6x minus 51. Then, isolating x, we could get 5x is equal to 71. And if we divide both sides by 5, we'd get x is equal to 14 and 1 over 5. Now, earlier I said I always prefer to work with fractions, but in this case, it may make it easier just to express this as a decimal. Can still carry on working with fractions, but it might be easier to express this as a decimal. Okay, now if x is equal to 14.2 at the point of intersection, to find the y-coordinate at the point of intersection, all we need to do is to substitute this value of x into the simpler of the two linear equations, and then find out what that value of y is. of 11.4. So our coordinates of r, the x value of r is 14.2, and the y value is 11.4. And there you've done it. You found the coordinates of r, the point of intersection of the two normals to y at the point P and the point Q. For part B, we need to find the area of triangle PQR. This is a slightly uncommon question, but a very good question to go through because what we learn from it can be applied in different types of questions that we may be faced with in exams. Okay, so if we remember, the point P is the point 4,8, the point Q is the point 9,1, and the point R is the point 14.2, 11.4. It will be very helpful for us to sketch these on a grid. So let's just mock up a little grid for us here. Remember, just a sketch, not an accurate plot. And 4,8 we could possibly seems reasonable to put it over there. So here would be the point, there would be the point 4,8. There's the point P. Q would be the point 9,1. So it would be a lot further along than this, but lower down. So there would be the point. Q would be 9,1. The point R would be further along than Q on the x-axis and a little higher than P. So we could put the point R up here. There's R, 14.2, 11.4. And they want us to work out the area of the triangle PQR. So let's draw that triangle there. We want the area. That is our goal. We want to work out the area of this triangle PQR. Now that we have our points P, Q, and R sketched onto our plane, something that will help us calculate the area of this triangle PQR would be drawing a rectangle around this shape, around this triangle, making sure that the perimeter of the rectangle passes through each coordinate of the vertices of our triangle. Now let's label the corners of this rectangle. The bottom, let's actually call this rectangle, let's call it A, B, R, C. And let's work out the coordinates of each corner. So the coordinates of A is in the same vertical line as P. So it would have an x-coordinate of 4. It's in the same horizontal line as Q, so it would have a y-coordinate of 1. B would have the same x-coordinate as R, which is 14.2, and the same y-coordinate as A and Q, which is 1. The coordinates of C, would be the same y-coordinate as P and A, which is 4, but the same y-coordinate as R, which is 11.4. Yep. Now that we've got that sketched up, it's going to be very helpful for us to work out the area of the triangle. Let's just make some space to work. So I'm just going to shrink that down and move it one side so we've got some space to work on the right. Now, what we're wanting is we're wanting the area of triangle PQR. And hopefully we'd be able to see that that would be the area of this rectangle minus the area of all these little triangles on the outside of PQR. So to work out the area of the triangle PQR, we would want the area of the rectangle ABRC, and from that we would want to minus the area of triangle AQP. Combined with the area of QBR, combined with the area of triangle CRP. Right. Now, although that might seem quite a lot to do, the calculations to work it out are fairly simple. Yeah. So to work out the area of the rectangle ABRC, that would just require us multiplying the base of the rectangle by the height. The base of the rectangle is the length of the line from A to B, which would just be 10.2. That comes from 14.2 subtract 4. And we would need to times that by the height of the rectangle, which would just be 10.4, which comes from 11.4 minus 1. So that would give us the area of the rectangle. Now we need the area of the triangles. Yeah. So the area of the triangle AQP would be a half multiplied by the base length, which is 9 minus 4, 5, times the height, which is 8 minus 1. And that there is the area of triangle AQP. We'd find the area of triangle QBR in a similar fashion. 14.2 minus 9 would give us 5.2, and we'd have a height of 10.4. And then we also have to get the area of triangle CRP, which its base, we would take the base would be, that is 10.2. Sorry, I forgot to put that little half in. Let me just correct that. It would be a half times 10.2 multiplied by the height, which would be 11.4 minus 8. So that would be 3.4. Something we notice that every a term inside the bracket has is this half. So you could factor that out if you wanted to. But because we have all numbers in this expression now, you can enter that into your calculator in one go, and we'd get a final answer of 44.2 units squared.